nanohub.org.
Online simulation and more for nanotechnology.
All right. So this is the report of the socio-technical resilience breakout sessions. So we discussed a couple of questions. The first question was essentially, how do you define resilience, resilience of a socio-technical system in a measurable way? So we started, these are some comments that you can find in the summary. Resilience is hard to define at the abstract level. So we're looking for an abstract definition that can be applicable to different socio-technical systems. And that's because it has multiple perspectives, and most importantly, it requires the ability to overcome system inertia and initiate a productive change. So there's this adaptivity element that needs to be in there. And it's to accommodate the role of the human in the system. And then again, we ask ourselves, resilience from the perspective of whom? Is it the users? Is it the stakeholders? Is it some decision maker in the system? Is it the system itself, if that could be said? We discussed that, we said that resilience should be considered at the design phase, but then again, you don't really know what's going to happen to your system when you put it out in the field. So the definition must change as the future unfolds. Anyway, based on that, I basically pulled out of my behind a definition of something that is not resilience, but let's say something that you could use to build resilience measures. So, for any socio-technical system. So we said basically list all known functionality measures of your system, the things that are interesting to you, quantities of interest that you can measure and correspond to the functionality of the system. Define acceptable functionality levels, and then list the potential disturbances and your beliefs about these disturbances, like earthquakes happening, hurricanes about to happen, and what is the probable intensity of these. And using that, you can define something that again called conditional T-resilience to make it fancy, but it's not resilience, it's conditional T-resilience. And it's the probability that the system's functionality is within acceptable levels, conditional on a hazardous event after a given amount of time. But it's not a number. It is the entire joint distribution of your functionality variables. So you could use this measure, this probability distribution, if you have it, to come up with specific scalar measures of resilience that characterizes you as a user or decision maker or the system itself. So the idea is that if you had this probabilistic assessment of your functionality after an event, you could use it to define a resilience measure that you could use in decision making. But then again, this is very static. So what about adaptability? How can adaptability come into the picture? So then we said that the system really should have inside it an intelligent agent or a group of agents or a committee, if you like, okay, that continuously monitors these things. So it basically continuously changes the functionality measures, continuously changes the acceptable functionality levels, continuously monitors the possible disturbances that can occur, and basically this entity has a model of the system. So it's an entity inside the system that has a model about the system and runs hypothetical scenario about what can happen to the system. And this is what would provide adaptivity in a socio-technical system. Now, in actual socio-technical systems, this is an actual group of people inside the system arguing about the system. Anyway, so what is the modeling fidelity required for designing, monitoring, and operating resilient socio-technical systems? Here we basically listed everything. Okay, this is expected. So the agent-based models, because we have to deal with humans, statistical models, because we have to analyze data. Of course, there are physical models on the background. It's extremely complicated, okay? The basic problem that comes up all the time is modeling human behavior. And so we need to understand human behavior better And no, because humans are components of our system, but then again, socio-technical systems have so many humans inside them that you cannot possibly model every single one of them. So the question is, what are effective descriptions of these human behavior models, if there are any? What is the role of humans in socio-technical systems and how they can be modeled? So humans are users of the systems. They are decision makers within the systems, and in many socio-technical systems, they can change the system itself. And there is a great variety and heterogeneity in human behavior. As I said, we cannot model everyone. We need effective models if these are possible. Most importantly, we need to start thinking about the human elements of the system that make decisions about the system, and think about the incentives of these human elements, and make the incentives, and by human elements, for example, let's take a city and the politicians making decisions about the city. The incentives that you give to these politicians are part of the city system, and you should change these incentives so that these individual's goals align with the system's goals. All right. So, how can you do that? What sort of theories do you need to do that? And so on and so forth. Next, what data are essential for calibrating socio-technical system models, and how can such data be collected? The answer is everything, but you can't. All right. So how do you prioritize which data you collect? Human behavior data is where we're mostly lacking. But at the same time, when you're collecting data about humans, you need to worry about privacy issues. You need to, yes, you need to get IRBs and all that. It is not, there are ethical questions. What else? There are also security issues. If you collect all this data about your system and you store it somewhere, then maybe if somebody gains access to this database, they may find new ways to harm your system that didn't exist before you started collecting the data. And I think with that, all the other questions are unanswered. Okay? So that's it. All right, guys.
So I'm going to report discussion from two breakout sessions. So one is from the new one. It's for cyber. So basically, we are talking about what are the challenges from the cloud, data center, and the edge. So basically, we look at the entire landscape of computing. They involve as tiers, as we know, right? So we see there are no slides. Sorry, no slides. Yeah. So there are existing challenges that are still unsolved. For example, the DDoS attack. For example, as we move computation to the edge, we are going to put computation on the base station, for example, on the edge. So how do we build the infrastructure so they are more resilient to all kinds of threats? And when we move applications to the edge, how can we build resilient applications so applications can handle failure, can handle this unpredictable resource shortage? We also talk about the resilience challenge to users' data, because as computation are moving towards the edge and to end devices, so we put more trust to the computation that is near us. How do we ensure that our privacy is respected? There are definitely some classic approach like differential privacy, but that's not always working. So there are interesting points on domain-specific data resilience. For example, genome data, they're highly sensitive. They have private information, so you cannot treat them with classic approach. You cannot add noise to this data because people don't know what will be the outcome of this noise. Okay, so these are the challenges. So we also talk about the approaches. There are existing classic approaches. For example, from systems and software engineering side, you can ensure high resilience with more resources. Basically, you keep adding resources, then you have more replications. You can do extra checkpointing of the system state. Then you are more resilient to failures. So there are also approach like stress test, right? So you basically have application, you really want it to be resilient, then you, in the lab, you come up with a very thorough suite of test cases and you stress test the application. So hopefully you can predict all the failure cases that will happen in the wild. So then in recent years, there is a growing interest in fuzzing test. So people come up with all kinds of ideas to build this fuzzing strategy. But maybe that is still not enough, right? In certain environment, you really want very strict guarantee. Then in that case, a formal method could help. Basically, you can mathematically prove, you can certify a certain piece of software hardware stack is, it will not fail. It will be for sure resilient to any situations that you have in mind. However, resilience, the formal method for resilience is often at odds with scalability because we want a performance and it's not easy to build a formally verified application or system that also runs fast, that also scale. So then the composable, right? The idea of making system composable, that makes a lot of sense. You can certify individual part of the system, then compose them. Then by doing that, hopefully you can build a scalable, formally proved system. So theory can help too. Basically, we also need theorists to build a more thorough framework to help build the resilient computer systems. Okay, then we also talk about a data-driven approach. For example, how do we mine massive set of error logs to isolate, to localize the bugs in a complicated software stack? How do we spot the anomaly in the field? Right? How do we identify the rare events as soon as possible so we can avoid the rare events to evolve to become a huge failures? So with all these things in mind, we still realize there are some big hole in today's software hardware stack. So for example, for network. So network these days is designed to be resilient against failures, resource shortage, for example. It's not to be designed against attackers. So that's why we have so many, for example, botnets for IoT devices. However, we are not even sure what will be the correct behaviors of the network, right? Because there is no such specification. So in that aspect, then we probably should first come up with specification, then policy may help, right? You should mandate certain properties of the network. Then by doing that, you can come up with a better design. So that's a very brief overview of the cyber part for resilience. So basically, we identify open challenges and we identify known classic approaches, and we also identify some unknown black holes in today's software hardware stack. Okay, so that's I'm gonna change the gear a little bit, talking about a very blue sky topic that we just talked about. So this is called the planet scale IoT. Okay, now you may have many questions. So we also had many questions. So first is are we going to have such kind of thing, right? So planet scale IoT, is it gonna happen? So we talk a lot about the applications, the useful scenarios. So one consensus is IoT is going to happen for sure. For example, we have Amazon Echo and Google Smart Home in many of our homes every day. Then people mention that in power grid, right? This is a very interesting example. In power grid, this planet scale IoT is already happening. So basically, this is for load sharing. When the electricity provider notice there is a need to share the power load, they will actually they will send messages to the end users, ask users to turn off, for example, their watches and dryers, or defer their certain tasks. So actually, as you can see, there is a sensing, there is a closed loop for both sensing and actuation. You can argue that is planet-scale IoT, and it actually proves the value of such large-scale IoT systems. So people also mentioned there could be interesting applications like smart cameras. So those cameras can be deployed in the wild. There could be many of them. They could automatically recognize interesting events or anomaly, for example, in the crowd. Then if there's something bad happening, for example, there's an Amber Alert, it could automatically send messages to a big crowd. So that also helps. People also mentioned citizen science is also is very interesting domain for this planet scale IoT. For example, we can have many low cost weather stations deployed in the field or in people's home, in people's backyard, then by combining that information with satellite information, you can paint a much complete picture of the climate, of the weather. So that helps as well. Then what will be the resilience challenges, right? So this is more open-ended question. So for example, when you have such large-scale IoT devices, you inevitably have many sensors. Those sensors, they are very noisy. They could generate data of varying quality. How do you deal with this bad data? How do you ensure your result is still resilient when the data could be bad? So the challenge also comes from the large scale. For example, you can have very heterogeneous devices, right? How can you operate such a large base of devices? And the device state could be very different, right? Some device may be operating, some device maybe they are down, they can operate from time to time, or some device they may generate wrong data, or even they cannot generate any data at all. Another challenge would be when we have such a big data, how can we drive control decisions out from such big data? So one classic approach will be sampling, right? Then what sampling strategy will you have? So sampling also comes in hand with this quality of service and distributed control. So when you do sampling, you almost guarantee to optimize for the average one. But how do you optimize for worst case, right? How do you provide a meaningful quality of service? So that's also an open challenge. So one interesting thing that people talk about is with this planet scale IoT devices, we often have human in the loop, right? The example I mentioned earlier, the power grid case, human will have to make decision whether to turn off their the washer or dryer in their home. So human cannot be easily modeled, right? Because human, we often make irrational decisions. So when a lot of people are in the system, they can make very different decisions. So that irrationality will bring a lot of uncertainty to the system. So that will make system very unresilient, right? So how can we design mechanisms? How can we design policies to make sure our system is still resilient with a large crowd of irrational people in the loop, right? So that's a very interesting question. I think one insight we have is there should be a policy for human, okay? And the policy for human should be as simple as possible. Basically, that makes the system more resilient as a planet scale IoT. So that's my take, incomplete take from these two discussions. Okay.
All right, so in the breakout session in the morning was on smart cities. Now, I started by saying that cities by definition are in some way smart. Otherwise, the hunter-gatherers wouldn't have made their first cities. And ever since then, from the small cities that probably had just a few thousands of people, now there are mega cities like Tokyo and other places, which is the empirical proof that cities add value. But until about 15 or 20 years ago, people didn't know what is it in the city that makes things valuable. And it turns out what cities do, that it uses the resources sublinearly, that the roads, the number of police, the street lights and other things that you need, because of the shared resources, it increases sublinearly with city size. But the output, which is the productivity, the patterns and other things, that increases superlinearly. That's why cities form. But the sad part of that interconnectedness is also that crime and other bad things scales with the same superlinear exponent. So this issue about security in cities, cybersecurity is new, but the general issue about security, that how do you handle when a lot of people are around and bad people are around too, then how do you handle them? This is a general problem. I think we can learn from previous things as well. So there are 5 things that we started by discussing. One was this communication. In the city, all this, you have to provide high bandwidth services to different people. Energy, how do you sort of smart meters and other things so that every house utilizes the energy that it gets in a optimized way. Then the issue about government, then transportation, all this cars, smart cars and all, these will come in. Environment, pollution in big cities is a big deal, and smart cities will not be immune from it. So these are the things that one has to think about. And the reason people move to cities, one thing that was mentioned was that because of jobs, because of education, because of healthcare, these are the reasons why people move to cities. And so therefore, in some way, one has to sort of coordinate all this. So I'll just mention 3 things, then I will stop. I know it's late. One thing that we discussed was that the systems, in many systems, are already very highly interconnected and very complex. So I think Nali, right, she mentioned that she had to take her mother to a hospital in Boston, and she was surprised how interconnected the pharmacy is with the hospital and with the whole network, that how interconnected things are. So things are already happening even without the security guarantee and cyber robustness. And so some of the proposed solutions were that it should be hierarchical. Any new design should be hierarchical, small groups building on top of larger groups, and that will essentially ensure privacy as well as hacking and other from there. The other one was that people often overbuild after a disaster like an hurricane or flooding. People overbuild a city, and that next time when the city faces a disaster, the cost is even more. So how to build cities more adaptively. And then a final thing was not to over-optimize a city, because once you over-optimize, those systems are very fragile. And so don't overestimate, and how to bring in mathematical theories and foundational theories to this problem is something that there were a lot of interest in. The second point was James made this point very clearly, that these smart cities will have lots of interconnected pieces. And individually the pieces may be just fine. But think about, let's say you have smart vehicles, and you have a power grid, 2 networks. But let's say there is a storm warning, and everybody wants to put their smart cars or electric cars and want to charge it. So that will simultaneously bring down the grid and stop people from charging their car. So systems that are individually stable may not remain stable when they are connected. And this aspect is not being, at least that's what he was thinking, that is not being addressed, and this is something one must be sort of very careful about. And finally, I think the discussion about cities brought in, I think Miko made this point, that we should not just be thinking about smart cities. There are also resource-limited communities, distant communities. Those are also a very important part of the equation. Smart city, you can do many technological solutions, but what do you do in resource-limited one road to a place? What do you do in those cases? How do you make those communities robust? And that, she thought, was a very important consideration. And some of the solution was repurposing the resources. For example, all the telephone booths, old telephone booths in UK are being repurposed before being sort of providing local information, telling which park bench is free, what is the weather, make free local calls, and so sort of repurposing the systems may actually be very helpful. So this is the third thing that we discussed. But we have a long report. There is a lot of interesting discussion. I'm just summarizing it for you. So that's all I had. Thank you.